A very good morning to all distinguished guests, experts in the field, and technology enthusiasts gathered here today. My name is Chiew, and thank you for attending my presentation on a comparison between Fourier and Hadamard single pixel imaging in deep learning enhanced image reconstruction. This is the flow of today's presentation. First, I will bring you all through a brief introduction of what single pixel imaging is, and followed by the principles and methods of single pixel imaging. Then I will go through the conducted experiments and our exclusive findings. Finally, I will conclude this presentation and mention our honored sponsors. So first, what is single pixel imaging? Single pixel imaging is a system that works by capturing high quality 2D images using a single photodetector. Normally, a spatial light modulator is used to generate the speckle patterns, and a bucket detector is used to collect the reflected light signals. So here you can see that we use a DMD, digital micromirror device, as the spatial light modulator, and we project the binary speckle patterns onto the object. Then the reflected light signals are collected by a bucket detector. Then the collected analog signals are converted into digital signals using a digital to analog conversion data acquisition device and transmitted to a computer for single pixel image reconstruction. Out of so many schemes, Hadamard single pixel imaging and Fourier single pixel imaging are the most notable ones due to their high imaging speed and accuracy. Existing comparisons are carried out under conventional image processing settings showed that Fourier single pixel imaging outperforms Hadamard single pixel imaging in terms of imaging efficiency and inadequate sampled scenarios. Recently, the advancements in deep learning and efficiently solve the inverse problems in optical imaging applications. For example, convolutional neural networks can utilize lower sampling ratio while recovering the lost signals in compressed sensing. Hence, in this study, we compare the deep learning enhanced Hadamard single pixel imaging and Fourier single pixel imaging using a nonlinear activation-free network called NAFNet. Now let's look at the principles of Hadamard single pixel imaging and Fourier single pixel imaging and the methods utilized to produce a fair and reliable comparison result. In Hadamard single pixel imaging, we use the Hadamard spectrum as the measurements for single pixel image reconstruction. The similar expression shown in both the forward and inverse Hadamard transform shows that the Hadamard transform is a symmetric, unitary, and separable transformation method. In the Fourier transform, we use the sine and cosine transforms to decompose the scene into spatial frequencies, which represent the single pixel measurements. Hence, both Fourier single pixel imaging and Hadamard single pixel imaging follow the same working principle where patterns are projected onto the scene to encode the graphical signals, and the inverse counterpart is applied computationally to reconstruct the single pixel image. The adopted CNN model is a nonlinear activation-free network called NAFNet. NAFNet is a standard unit architecture with layer normalization, gated linear units, channel attention for improved performance and efficiency. To train NAFNet, we use the reconstructed 100,000 single pixel images from the SDL-10 dataset and split them into portions of 8 and 2 for training and validation sets. We use bilinear interpolation to downsample the images to a resolution of 64 by 64 to satisfy the requirement of Hadamard single pixel imaging for a power of 2 image resolution. In short, we reconstruct the images with Fourier single pixel imaging and Hadamard single pixel imaging and fit them into NAFNet for image enhancement. We compare the NAFNet enhanced Fourier single pixel imaging and Hadamard single pixel imaging with 4 sampling ratios, namely 1%, 5%, 10%, and 20%, which corresponds to the number of measurements shown here. For evaluation, we use the standard PSNR and SSIM metrics to show the different aspects of the NAFNet improved images. Now let's look at the comparison results. Generally, SSIM has larger improvements as compared to PSNR. The marginal PSNR improvement is due to the low sampling ratio used, which limits the raw signals provided to NAFNet for image restoration. On the other hand, The SSIM improves more due to the local convolution filters in NAFNet, which removes the pictorial artifacts in Hadamard single pixel imaging and Fourier single pixel imaging. Looking at the improvement trends, the general PSNR and SSIM improvements increases when the sampling ratio decreases. However, there is an inconsistent trend observed for the PSNR improvement for FSPI, where the PSNR improvement increases when the sampling ratio increases. This is due to the ringing artifacts in Fourier single pixel imaging. In single pixel imaging, because the ringing artifacts in Fourier single pixel imaging affects the image clarity. Now let's look at the model convergence for both Hadamard single pixel imaging and Fourier single pixel imaging at different sampling ratios. Consistently, when the sampling ratio increases, the amount of semantic features input to NAFNet increases, which eventually leads to improved model convergence. As shown here, NAFNet FSPI requires more iterations due to the ring artifacts, because the ring artifacts affect the image clarity. Next, the detailed numerical results shown here shows that the Fourier single pixel imaging is generally better than Hadamard single pixel imaging in reconstruction performance, similarly for their enhanced variants. In terms of inferencing speed, Hadamard single pixel imaging is faster than Fourier single pixel imaging due to its binary sensing patterns. Then, adding the image restoration delay using NAFNet causes a 11 FPS and a 7 FPS drop in both NAFNet enhanced HSPI and FSPI respectively. However, we can still achieve real-time imaging performance with enhanced accuracy. Visually, NAFNet enhanced Fourier single pixel imaging and Hadamard single pixel imaging have better accuracy even at lower sampling ratios. This is because at lower sampling ratios, NAFNet recovers the contextual features, which improve the general structure of the image, while at higher sampling ratios, NAFNet refines the lower level features, such as the edges and corners, to achieve higher image clarity. Nonetheless, NAFNet FSPI still outperforms NAFNet Hadamard single pixel imaging, but with a slightly lower frame per second. So in conclusion, there are existing comparisons between Hadamard single pixel imaging and Fourier single pixel imaging. However, they were made only within the conventional optical image processing setting. We hereby present the first known comparison of Hadamard single pixel imaging, Fourier single pixel imaging, and their deep learning enhanced variants based on NAFNet. Both Hadamard single pixel imaging and Fourier single pixel imaging attain considerable improvement in terms of with only a slight drop in imaging speed. But the interesting thing is that the PSNR performance gain of Fourier single pixel imaging shows a declining trend due to the ring artifacts that provides a better approximation of the ground truth signals even at lower sampling ratios. Lastly, I would like to conclude my presentation by thanking the sponsors of this work, which is the Malaysian Ministry of Higher Education and Monash University, Malaysia. I think that's it. Thank you for your attention. If you have further inquiries after today's presentation, you may email to us at the following emails. Thank you.